first came to CERN to work on in the 1970s. And then protons from there go both clockwise and anti-clockwise around the Large Hadron Collider. And there are 4 places where these needle-like bunches pass through each other. Atlas, where we are at the moment, CMS, the experiment I work on, as far away as possible from CERN, and 2 smaller ones called ALICE and LHCb. So I'm just catching up with where you got to, right? So here we are at the Atlas site, the colliding beams, 100 meters underground, an enormous shaft, and then this is the building we're in, I think, at the moment. So it's just the other side over there. There's this big hole in the ground, and the pieces of the detector came from all around the world, from the different institutes and universities that built them, sent down piece by piece, and it took them nearly 3 years to put them all together. People sometimes say it's like building a ship in a bottle, only this is a detector weighing 7,000 tons. I think the next one shows, that's what it looks like. I've mentioned, I think, to both groups that the detector is not a single detector, it's a lot of sub-detectors in layers to measure the different things. We want to catch all of the particles that come out of the collision so that we can work out what went on at a very tiny fraction of a second of the collision. You might think the best way to do that would be to build a spherical detector that completely covers the interaction point. But it's actually more convenient from building it and from taking it apart to do any maintenance or repairs, to build it as a cylinder. We call the central part the cylinder the barrel, and then 2 end caps poked in so that particles in all directions will be detected. The first thing we do in the very, very center is we have lots of little slices of silicon. As the charged particles go through the silicon, they produce pairs of electrons and holes, and they drift to the surface where there are very, very finely spaced metal electrodes, so you can measure the position to, I think it's 10 microns, 10 thousandths of a millimeter. And many, many stacks of those so that you can find the tracks of the particles. Not only the direction they're going, but there's a magnetic field inside which bends the tracks of the particles. One direction if they're positive, the other direction if they're negative. And the amount of bend depends on how fast they're going. The really fast particles will be quite straight, only a tiny curve. The slower ones will have quite a big curve to them. So by measuring the tracks of the particles, we can find not only where they're going, but also how fast. Strictly speaking, in case there are any physicists here, we measure the momentum rather than the speed. Then we need to know what type of particles there are. So there are 2 layers of what we call calorimeter. Calorimeter is just a fancy word for measuring the energy. We can distinguish between particles like electrons and their antiparticles, positrons, and gamma rays, very high energy gamma rays, which interact. If you have a lot of material there, they interact with the atomic electrons in the material. They knock the electrons forward, or they create electron-positron pairs, and those still have high energy, so they collide again and again and again. You need quite a thick layer of material to transfer all of the energy of the incoming particle into a large number of low-energy particles, a shower of particles, as we call it. And we can count how many particles in the shower because each of them gives ionization in the liquid xenon material that it's bathed in. So the number of particles in the shower is proportional to the energy of the particle coming in. That's how we measure its energy. That's the first layer. Then the second layer measures the energy of particles that interact strongly. The strong interaction is the one that holds the protons and neutrons together, holds them together in the nucleus. And so particles like protons, neutrons, pi mesons, k mesons, these don't interact so much with the atomic electrons, but directly with the nucleus. And they knock particles out of the nucleus. Again, these particles have high energy, so they collide again and again and again. So after a certain thickness of material, we've built up a shower. In fact, the material is a multi-layer sandwich. Sheets of iron, plastic scintillator, sheets of iron, plastic scintillator. The plastic scintillator gives a little flash of light for each particle that goes through. So we can count the number of particles in the shower, in this hadronic shower as we call it. Hadros, any classical Greek scholars here? Hadros means strong in classical Greek, so hadronic particles are strongly interactive particles. So we can measure their their energy by the number of particles in the hadronic shell. Then finally, there's two more groups of particles. The first group are called muons. Muons are just like electrons, but 200 times heavier. So they don't stop here. They're like cannonballs going through a box of ping pong balls. The ordinary atoms just don't stop them at all. They go right out to this magnetic field that circles round on the outside. On the movie you saw one of these coils being lowered down. And they're bent, their tracks are bent in this magnetic field depending on whether they're positive or negative. So we can measure their energy and whether they're positive or negative. And then finally, there's a class of particles called neutrinos, which hardly interact at all. They're not electrically charged, they don't follow this strong interaction, the hadronic interaction, they only follow the weak interaction, which is very weak, and so they just leave the detector without being seen. So how do we know that we've produced neutrinos? Well, by carefully measuring the energy of all the other particles and seeing if there's any imbalance. If there's more energy in one direction than in the other, then we know that that energy was carried away with a neutrino. And that's why it's very important that these people are here checking up on the performance of the detector, because if there was a dead region anywhere, and ordinary particles went into that dead region, we wouldn't detect them, we would confuse them with neutrinos. So that's why it's all got to be working all the time. So this just repeats what I've been saying. This is now a slice through the experiment. The particles collide in the center here, their tracks are measured, then the energy of the electromagnetic particles, energy of the hadronic particles, energy of the electromagnetic particles here in this brown bit, then the hadron particles, and then finally the muons, or perhaps a neutrino which isn't detected at all. And there's millions of individual detector elements here to measure each of these tracks. We sometimes say it's a little bit like a digital camera. Your digital cameras will have, 6 megapixels, 8 megapixels. I've seen people coming with quite professional ones with 12 megapixels. We have 40 million separate detector channels, 40 megapixels. And your camera takes a few pictures a second. Perhaps if it has a movie feature, it'll take 24 pictures a second. We've got to take 40 million pictures a second as the particles as the bunches go through each other. And just like your digital camera, you go home in the evening and you look at the pictures you've taken that day and you say, oh, that's a good one, that's rubbish, delete it, that's rubbish, delete it. We can't possibly store 40 million pictures a second continuously. We have to whittle it down. We can only store about 1,000 a second. So what we do is we have computers attached to the detector, 2,000 PCs worth of computers, analysing the data as it comes in real time, seeing which are the interesting collisions and which are the boring ones. The interesting ones, of course, are these head-on collisions, but the majority are these boring collisions where you have a glancing blow. In fact, it's worse than that, because protons are not really elementary. They're made of particles called quarks, held together with gluons. So it's really like colliding two bags of marbles, and what you want is a head-on collision between two quarks, or between two gluons. So we have to select those interesting events. We do keep a tiny fraction of the ordinary events, just to make sure we're selecting correctly, that we're not throwing the baby out with the bathwater. But we have to whittle it down from 40 million a second to about 1,000 a second. And then that data is sent to the CERN site, where it can be analysed later. And we don't even have enough computers at CERN. We've got 20,000 PCs in one big room at CERN, but we need 100,000 to analyse our data. So we're connected together to big computer farms, as they're called, all around the world. One here at Rutherford Lab in England, Brookhaven in the US, Fermilab in the US, Germany, Japan, and so on. So the tier 0, the centre here, is the CERN site, but we're connected together to all of these. Not just for storing the data, but of course for the computing power as well. And I can sit at my university and launch a job. I don't need to know which computer has time available or where the data is stored. That's all taken care of by the software. We call this the grid by analogy with the electric power grid. When you plug your toaster into the wall, you don't know whether the electric power is coming from a nearby power station or one the other side of the country. I don't need to know whether it's using computer power at Brookhaven in New York State and data stored in Japan. That's all taken care of, and the results are returned to me. If any of you are in the computing world, in the commercial world, this grid system is called cloud computing. If you've ever heard of cloud computing, that's what they do in the commercial world. And of course, this is not just available for particle physics experiments, it's available for other scientific purposes. For example, have you ever heard of protein chain folding? Proteins are made amino acid by amino acid from the recipe in the DNA molecule. So they're really a long linear chain molecule. But at each junction between the amino acids, they can fold and rotate. And you have to find the lowest energy configuration. What the protein actually does is it forms itself into a fuzzy ball of string almost. But to find out what is the most stable configuration, the computing that you have to do over and over again at each of these thousands of joints where they can rotate and so on is just mind-boggling. But if you need to design drugs, you need to know the exact shape of the protein molecule that it's going to operate on. So there is time available on this grid for people doing that, and many others. Atlas comes from 38 countries, 174 universities, 3,000 scientists. Okay, just a few more than ours. I like to... CMS, by the way, although it's only half the size of Atlas, is more than twice the weight. It's about, well, we usually say 12,500 tons. It's perhaps even a little bit more than that. We have not 3,000, but 2,500 collaborating scientists and engineers. And it took me a little while to realize that's still 5 tons each. 2,500 people, the detector, I can say 5 tons of that is mine, and so can the other 2,499 people.
I have a question.
Yes.
Why the Indiana is not included? Because it's a big country?
They are part of the other experiment, CMS.
Okay.
I suspect that they didn't want to divide their resources.
It's only Atlas.
This is only Atlas.
Oh,
yes,
right, yeah.
right there. I mean, there is a similar map for people. For example, we have people from New Zealand on CMS, okay. But not. Oh no, it is next that I want. I don't know why it went back. Yeah. So yes, people from the 5 inhabited continents. Actually, even if you were to add the CMS people and all the other experiments at CERN, there are experiments, not all of them using the LHC. Some of them use the protons from the smaller machines, the superproton synchrotron, even the proton synchrotron. But I'm afraid, even if you add them all together, a lot of Africa would look very white, which is a shame. Yeah. And I'm pleased to say that 2 or 3 weeks ago, they had an institute in South Africa with physicists from many African countries to tell them about particle physics. I thought it was a summer institute because it was back in August, but of course it wasn't summer in South Africa, so a winter institute. Right. So yes, this is the information you get from the individual subdetectors when you have a collision. And here's a projection of the tracks. Remember, they're curved to tell you how fast they're going. And there's actually no muons in this one right out. This one has 2 what we call jets, groups of strongly interacting particles, groups of hadrons. We think that's because in the original collision, 2 quarks were liberated going very fast. But quarks, you never see them on their own. They always combine with others to make protons and neutrons and mesons and so on. So you detect them by the jets that come out. This one I think has yes, this has a muon track. Set collision of a muon track. This one has a K-short. That seems to be the end. Okay, right. I've actually always been able to explain the detector outside with the mural before. I've never explored this presentation to its end. So now I know what's there. That was the short one. There are longer ones. How are we doing for time?